Hi everyone, how is everyone doing today? This is module 3, Fuzzy Control System Design. In the previous module, module 2, we have looked at several concepts of fuzzy logic. We have discussed some fuzzy logic application, namely in washing machines, automatic gear shift control, the elevator supervisory control system, and intelligent fault diagnosis of power transformers. We have also discussed fuzzy sets, membership functions, fuzzy operations, fuzzy relations, and fuzzy composition operation. In this module, we'll be talking about fuzzy logic controller. It's an application of fuzzy logic. By now, everyone should know what is a control system. These are some examples of control systems: cars, aeroplanes, trains, ships, robotic manipulators, and so on. Typically, this is how a conventional control block diagram would look like. These processes or systems are here. For example, if you talk about robotic manipulators, it would appear here in this block, and a controller would be here. So in this module, we'll be talking about fuzzy logic controller. Of course, from previous or other courses, you have learned PID control, self-tuning control, state feedback control, and so on, which will be in this block. The control objective is to design a controller such that output or control variable can be controlled by giving the desired signals at the input. So here, this output is also known as controlled variable, and some examples are as follows. So normally we would have a reference or set point which will be compared with the controlled variable that will generate the error signal. The error signal will go to a controller, and the controller will generate a control signal or manipulated variable. These are some examples of control. Alignment of the front wheel of a vehicle follows that of the driver's steering wheel, rudder of a boat, and so on. So for example, if we talk about the air conditioning system, the control variable would be the temperature of a room, for example, right? So the temperature of the room will be compared to the set point. Typically, we would set 24 degrees Celsius in Malaysia. So the error will be fed to the controller, which will in turn generate a control signal that would force the process or the system, or in our case the room, to have the temperature as we desire. So what are the factors that affecting our control system? Choice of controllers. So conventionally we used PID controllers, which is known to be effective, but perhaps it doesn't work all the time, and we have many other controllers as we talked about earlier. So all these different types of controllers have different performances that would affect the system differently. Tuning of controllers would affect our control system. For example, again, if we talk about PID controller, the value of Kp, Ki, and Kd would affect the performance of the control system. If we talk about fuzzy logic controllers, as we will see later, there are some parameters that would affect the controller performance. Any control system is not free from disturbances and noise. For example, once again, if we talk about our air conditioning system, the goal is to make sure the temperature is more or less 24 degrees Celsius, no matter how many people walk in or walk out. So those are the disturbances. So even in the face of disturbances or noise, a good controller would make sure the output is as desired. And how do we measure how good is our control system or the performance of our controller? Is by using some performance measure. Some examples would include the integral squared error, integral absolute error, and so on. So error is the difference between the reference signal and our controlled variable, and the integral squared error is just an integral of the square of the difference. So this will give you a summary of the control performance over a certain time range. So for example, if this is our set point and this is our control response or output response, the integral squared error will give us a summary of the error in average in this range from 0 to t, for example. So that will give us an average, but sometimes we would like to analyze in time domain. We would like to see the overshoot, the rise time, peak time, settling time, and so on. So for example, if we are designing a controller for an elevator system, we don't want to have any overshoot because that would imply that our elevator will go to slightly above the floor that we desire to get out, right? And probably we would like to have a slow rise time or longer rise time because a very short rise time would mean some form of discomfort in the elevator car. And these are some examples of control paradigms. And in AI, we have neural control, which is the application of artificial neural network. We have fuzzy control, which is the application of fuzzy logic. We do use genetic algorithms at times to tune the parameters of our controller and so on. And in other courses, perhaps you have learned state feedback control, H infinity, robust control, optimal control, and so on. And these are more examples. So if you think about your iron, most of us iron our shirts, the controller that works in our iron is the bang bang or on off control, which is evident from the noise that we hear. And we have learned PID control in your other courses. So why fuzzy logic control? So during the past decade, it has emerged as one of the most effective and fruitful research areas in the application of fuzzy set theory, fuzzy logic, and fuzzy reasoning. It was first proposed by Mamdani and Azilian around 1972. And since then, it has been applied and successfully products sold worldwide. So in contrast to conventional control techniques, fuzzy logic control is best utilized in complex, ill-defined processes that can be controlled by a skilled human operator without much knowledge of the underlying dynamics. So as we will see later, we can include rule base in the form of linguistic sentences in our fuzzy logic controller. So normally a skilled human operator doesn't really know about the underlying dynamics of our control system, but he or she knows how to control the system effectively. So we will try to, in our fuzzy logic control system, we can include that mechanism as we will see later. So the basic idea is to incorporate the expert experience of human operator in the design of a controller in controlling a process whose input-output relationship is described by a collection of fuzzy control rules. For example, if-then rules involving linguistic variables. This utilization of linguistic variables, fuzzy control rules, and approximate reasoning provides a means to incorporate human expert experience in designing the controller. So I would say this will be the main uniqueness or advantage of fuzzy logic controller, where we can include human expert experience in the form of fuzzy control rules. The benefits would be suitable for complex, ill-defined systems where mathematical modeling is too difficult. So if you remember in your PID controller, normally we would need the mathematical model of a system in order to tune the controller parameters effectively. So in fuzzy logic controller, You almost don't need the mathematical description of a system to design your controller, except for in simulation, but that works similar in PID controller. And in fuzzy control, we'll be able to design along linguistic lines by the usage of rules based on experience. This I would not say true all the time. Is it simple to design? Not necessarily. I have to be honest with you. Now, um, how do we design a fuzzy logic controller system? So this is typically how a fuzzy logic controller would sit in a control system. So as usual, we have a process or system or plant to be controlled. This is our control variable. We would have sensors to measure the control variable. The measurement will be compared with the measurement of our set point or reference. The difference or error will be fed into our fuzzy logic controller. In addition, normally we will also have the rate of change of error as another input to our fuzzy logic controller. So a fuzzy logic controller typically comprises four principal components: the fuzzifier, knowledge base or rule base, inference engine, and defuzzifier. And typically it's a two input and a single output component. It is usually a multiple input single output system. So a fuzzifier, the job of a fuzzifier is to convert crisp or real world values to fuzzy value. The defuzzifier will convert fuzzy value back to crisp or real world value to be fed to our process. In knowledge base, you would have information about our membership functions and rule base. An inference engine will determine which rules are fired given our inputs and how to combine those rules to generate a conclusion or control signal instantaneously. So this is the design process. First, we have to identify controller inputs and outputs as the fuzzy variables. So if you have a system that you want to control, you have to decide what are the inputs to your fuzzy logic controller and what is the output, right? If you talk about DC motor and you want to use the DC motor to track a reference angular velocity signal, then the input to our fuzzy logic controller will be error and change of error, and the output will be perhaps voltage or current. Next, we have to break up our inputs and outputs into several fuzzy sets. As we have seen in module 2, these fuzzy sets are represented by membership functions. And we have to label them according to the problem to be solved and set up the fuzzy variables on the appropriate universes of discourse. So this is what we call fuzzification, which means what is universe of discourse is the x-axis, right? So we have to set the range of values where our inputs lie. We have to configure or develop rules to solve the problem in terms of if-then statements. You have to choose inference encoding procedure. What is inference encoding? We will look at this later. If you remember from module 2, we had this fuzzy composition operations, right? Max min, max product. So those are the inference encoding procedures. And finally, we have to choose a defuzzification strategy. So if you remember what I said earlier, in fuzzification, we convert crisp values to fuzzy values. In defuzzification, we convert fuzzy values back to crisp or real world values. And often we have to tune the adjustable parameters. So you have to simulate your controller in your applied in your control system, and if the performance is not satisfactory, you have to adjust either the rules, you have to adjust the membership functions, the shape of your membership function, the universe of discourse, and so on. Now, how do we design a fuzzy logic controller for the following process? Some of this I will show in MATLAB example, so we'll just skip this for now. Operations of fuzzy logic controller. A fuzzy logic controller usually has two inputs and one output for a multiple input single output plant. These two inputs are used for accessing the current conditions of the process such that the necessary action can be taken by providing the correct control signal, which is the output. The inputs to the fuzzy logic controller is usually the error, which measures the system performance, and rate at which the error changes, or del E. And the output is the change of control signal del U. So if we are working on tracking problem, which means you want the output of your system to track a certain reference signal, and the input to our fuzzy logic controller. So this whole thing is our fuzzy logic controller. The input to our fuzzy logic controller is error. Error is reference minus output, and del error. Del error is present error minus the previous error, or ET minus AT minus 1. And the output is the change of control signal. So this is not always true. So this is where the design approach comes in. So sometimes it is the change of control signal depending on the system, and sometimes it's just U. That means the output of the control signal is not the change, but it's the control signal itself. We will see some examples on this. The role of fuzzifier, as I mentioned earlier, is to transform crisp values of error and del error into corresponding fuzzy values. And usually there are several fuzzy values of error and del error, for example, small, medium, big. From the rule base, the fuzzy values of error and del error determine which rules are to be fired through an inferencing algorithm. And we will obtain a fuzzy set of del U. So that's why we have to use a defuzzification mechanism, which will transform the fuzzy value of del U into a one crisp value of del U, which will be fed to the system. And the actual control signal is obtained by adding del U to the pass value of U, which is sent to the plant. So if our output, the output of our fuzzy logic controller is del U, then that value has to be added to the previous value of U, then we send it to the plant. What is fuzzification? It involves the conversion of input and output signals into a number of fuzzy represented values. So in the design process, first we have to choose appropriate membership functions to represent each fuzzy set. So for example, if we have error as one of the inputs to a fuzzy logic controller, we have to decide how many fuzzy sets error should be partitioned into. So it could be 3 fuzzy sets. So therefore, error is partitioned into small, medium, and big. We have to label them, and we have to set up the fuzzy sets on appropriate universes of discourse. Okay, so you have to make sure you have to choose proper membership functions for the fuzzy sets. And some examples of membership functions, as we have seen in module 2, would be the gamma function, the L function, Gaussian, and so on. And you have to set the range of these membership functions. You have to determine the width and center points of the membership function judiciously. So this is often, so in the beginning you just set some values, and once you simulate and you obtain the results which is not so satisfactory, you have to adjust the width and the center points of the membership functions so that you get better results. Consider a fuzzy rice cooker, which means we apply fuzzy logic controller in a rice cooker. So what do you think are the inputs to the fuzzy logic controller? Right, so this is how the rice cooker would look like. You have rice container with water and rice, heat sensor to measure the temperature of the water. It will go to a fuzzy controller, and fuzzy controller will generate control signal to the heating coil. So the goal here is to cook the rice optimally, right? So what are the inputs? So perhaps the two best candidates of input variables in order to make the output decision would be amount of rice and temperature of rice. So why? Perhaps this is the most logical choice of inputs. So if you have more rice, then perhaps you have to cook longer and generate more heat, I guess. And the temperature of rice or the water will determine how much heating you have to provide. So the output of your controller here would be the rate of heating. So this is the first part of the design, right? Next, you have to partition each of our inputs and output quantities. So note that these are our inputs and this is our output. Sorry, this is our output and these are our inputs. We have to ask these questions. So how many fuzzy sets should each be partitioned into? For simple problems, we can start with 3, but normally we would have 5. As we will see later, the higher the fuzzy sets, the more rules you have to determine. And what will be the correct labels for each fuzzy set? And what are the membership functions that you have to use for each of these quantities? So this is the output, right? Rate of heating. So for simplicity, we decide to have 3 fuzzy sets, and the label is low, medium, and high. And we had to decide the type of membership function that we want to use for each fuzzy set. For example, low, this is the L function. This is perhaps the gamma function. This is the triangular membership function. We have to set the universe of discourse, which means what is the range of the rate of heating, what is the minimum and the maximum value. For simplicity, you can have 0 to 1 or -1 to 1, and in the block of the simulation model you can add a gain to be adjusted later. And these are our inputs: amount of rice and temperature of rice. Again, we have chosen the L, triangular, and gamma functions, and we have labeled our fuzzy sets low, medium, high. So what if we have 5 fuzzy sets? Then some examples of the labels that we can use would be negative medium, negative small, 0, positive small, and positive medium. And it's often helpful to have it abbreviated like this: N, M, N, S, Z, E, and so on, because this would help us when we develop the rules later on. Now consider an air conditioner. How do you design the fuzzification component of the fuzzy air conditioner system? First of all, we have to decide what are the inputs and what is the output of our air conditioner, or rather the inputs and output of our fuzzy logic controller. So normally in air conditioning system, we would like to track our or regulate the temperature of the room. So assuming the output of our system is temperature, the inputs to our fuzzy logic controller should be error and change of error. So usually fuzzy sets are overlapped, by about 25%. What do we mean by overlapping? Is basically this, right? So the fuzzy sets the overlap, low and medium, the overlap by a certain amount here. It has to be overlapped in most cases. It can be observed that in fuzzy logic control, the transition from one fuzzy set to another provides a smooth transition from one control action to another. If there is no overlapping, then the control action will resemble a bivalent control. The transition from one error region to another is rather abrupt. On the other hand, if there is too much overlap, there would be a lot of fuzziness, and this blurs the distinction in the control action. So basically what it says is that you have to set the overlap accordingly to get desired performance. After simulating or after applying in the actual system, if you notice that the controller doesn't perform as you desire, perhaps you have to change the amount of overlapping. So this is what is meant was meant earlier when we say that we have to adjust the center point and the width, right? By adjusting the center point and the width, you will be controlling the amount of overlapping between these fuzzy sets, and that would affect the controller performance. For simplicity, we can choose the same triangular membership functions for each of the fuzzy sets of all fuzzy variables. So this example shows the membership functions chosen for two fuzzy input variables and one output variable and controlling an inverted pendulum. So normally, by just choosing a triangular membership function for all of the fuzzy sets, and all of the variables would work just fine.